For example, the derivative is positive here, that means it's increasing there, right? Right? And if I find out, and I already know that it's flat here, right? And then if I find out that the derivative was negative, then I know that it would look like that, right? So that's another way to know whether this is a relative minimum or maximum or neither, right? If it's positive, flat, negative, that's a relative maximum. If it's negative, flat, positive, that's a relative minimum. If it's like this, then it's neither, right? So we can also use that, right? So I think that might be easier in this case, I hope. Yeah, maybe because the derivative is a little easier to work with. It's not as complicated as this thing, right? It's generally going to be one level simpler. Not for e to the x though, right? E to the x doesn't do that. But otherwise derivatives are like one level simpler usually. Not for cosine and sine function either. But for this one, this type it is. So anyway, this is the derivative. So what we could do is we could put in, actually easier than 1 is 0. Right? That's easier to work with than 1 even, right? So we could put in 0 into here. What do we get? 0, 0, 16. So the derivative is positive. So I know that it is like that, and I know that it's like that, right? Now I can do, what's an easy number after 2? It has to be less than 8. So, well, 5. Okay, let's use 5. So 25 minus 50 plus 16 is what? Is that positive or negative? Negative. So I know that it's like this. Whoops, I drew that wrong side. It's here, flat, there. Right? Okay? And we could do the rest of this also. Okay, let's do the rest of it. So I know it's flat here. So I just have to check here. So let's try 10. So what do I get now? 100 minus 100 plus 16. Positive. Right? 100 minus 100 plus 16 is positive. So I get that. Okay, so I think that was easier than plotting the points. Right? So we get that the shape is like that. Right? So that tells us that there are relative maximum at the first point 2 and a relative minimum at the other point 8. Right? Okay? So that's useful. You know, we found relative maximum minimum. If this was profit, that might be useful. You know, especially like if you said, well, you know, I'm limited in terms of the number of things that I can produce up to here. I can't produce more than that, say, for example. So then you say, oh, well, then I should produce this amount to achieve the maximum profit. Right? So that could be useful. Now, the thing is that you should always ask somebody who presents this way of thinking to you is, yeah, that's really cool, but where in the world did this come from? Who gave us this profit function? Suppose this is the profit function, right? How can anybody make up that? You know, where's that really, you know? How do I know that profit behaves according to this formula, right? That's not realistic to know that, right? Nobody can know that. So this is like, suppose that profit behaved like this, right? You know, or let's assume that, you know, this is a decent model for profit, and then let's work with it. Let's derive some information from it, from our model. But you always knowing that, you know, you started with a suppose at the beginning. Suppose that profit looks like this. You might have some data, you know, that has some kind of, you know, like this. Then you kind of try and fit a curve to it, try and come up with a formula for that curve maybe. maybe you can do something like that, basically guessing your way through it until you come up with this formula. And then you can say, oh, let's deduce some facts based on that. Okay, but all the while, remembering that how you got this formula was by guessing. Okay? But still, it's kind of interesting, right? And it's a little bit tantalizing. And that's probably why people do it, because they believe that they can, wow, look what I can do. I can show the maximum profit, right? But you should always have it in the back of your mind. That's how I think, for example, the market crash in 2008, which was already 10 years ago, but there was a huge market crash in 2008, and that came from people sort of believing the mathematicians who were working in the banks, who came up with a whole lot of exotic, this is my interpretation, it's my cynical interpretation, but who came up with a lot of exotic formulas for pricing things. And they came up with all this stuff that you guys might learn about in your finance classes, like this, what's called the Black-Scholes model that tells you how to supposedly price an option and all this stuff. But I think you should always look for the hole in it. I haven't studied it enough to identify the hole in it, but what I mean is you should always look for the part that's saying, how did they get this? Isn't it just a theory? Anyway, so they had like this so-called Black-Scholes model, and then they make it super complicated by doing all kinds of manipulations to it and a lot of stuff. And they mesmerize their clients, because who can understand that stuff? Even the guys that wrote it, if they share with somebody else, the other guy probably doesn't understand it. Because it's just kind of like one guy following a train of thought for a long time and coming up with, a lot of implications and so on. So anyway, people believe that, and so they invest lots of money in it, but it was all based on something that wasn't true. So they'll project what's going to happen into the future, right? But it wasn't solid, because it never is solid, in my view. It can't be solid. It's just a guess. I could even say, even Newton's theories, which talk about how things fly through the air. If you shoot a rocket, it's going to go like this and come down, and the shape is supposedly a parabola, right? And but then that's only true, if there's no air friction and all this stuff. And maybe it is true, but anyway, I tend to want to think like all theories are theories. They're not. One thing I realized, I've been struggling with this question for a long time, is that there's a difference between the word proof in math and proof in science. And I never really had it clear in my mind, actually, but I think it's true. When we prove something in math, it's definitely true. But it's always based on a bunch of assumptions at the beginning. But the deductions from here to here, it's true. We always say, given this, then we can get to here, and it's called deductive reasoning, right? And that's always true. But when they say they prove something in physics, it's never true. I mean, maybe I'm wrong, but this is what I think. I mean that it's always only based on evidence, right? And evidence can always change, right? It's only what we know, right? So it's not the same thing as a mathematical saying something is proved mathematically, right? There's a difference, right? When we prove something mathematically, it's true, based on the assumptions that we're given. But when they say, we know something, a physicist has proved that this is true, never, no way. It's true now. Probably not going to be true in 20 years or 50 years. And not just because of that, but just because it's just based on evidence, not the same thing. So you take some evidence, maybe you can make mathematical deductions based on that evidence and come to another conclusion, but you're really starting on pretty much shaky ground, no matter what. So, that's my sort of radical view, but that was one thing that I had a professor kind of instilled that kind of thinking in me, I guess, a long time ago. Anyway, sorry about that. But going back to here, why did I even bring... because we were talking about profit, right? And I said, where can you get this profit function from, right? And that's the same idea that I was just saying, right? That it's only kind of guessing. Anyway, once you have it, though, you can make all kinds of conclusions about it. Okay? So, anyway, so let's get focused back on the math. So the math is, what's the idea? If you want to find the local minimum and local maximum, what's the steps that we follow? First, we find where the derivative is 0. And then we want to decide whether that's actually a local maximum or actually a local minimum or neither. And how can we do that? By looking at the derivative just to the left and just to the right. And that will do it, right? So that's called, that whole thing that is called the first derivative test for finding maximums and minimums. Okay? Does anybody have any questions about the first derivative test? Okay. Now, we have another way to do it, which is called the second derivative test. So we want to learn that. So that is based on this observation. So first let's get this observation, then let's see how we can use it to do the same thing that we wanted to do before, to find the maximum, local maximum minimum. Let's get this observation first. Let's see what somebody noticed first. Suppose that you have a curve, let's say it looks like that, again. Okay. So from here to, say, here, actually anywhere, but say from here to here, that's called concave up. Okay, concave up means you can pour water into it, and it will stay in there. But from here to, say, here, for example, if you pour water on that part, this is going to fall off, right? That's called concave down. Okay, so does everyone understand these terms? Concave up and concave down. Now, is there anything that we can do with our tools, which means the derivative, that help us to know when a curve is concave up and when it's concave down? So let's see what's happening. So let's think about the derivative. So going back to the same idea as before, let's say here's A, B, C, D, E, let's put E here, okay, E here, F, I better not use F, F, G, here, H, I, J, K, okay, that's enough. Okay, so let's think about the derivative at A, B, C, D, and so on. Okay, so what's the derivative at A? Well, obviously we can't have a number, you don't know the answer to that, but can you say whether it's positive or negative at A? Oh, it's negative, right? The slope is negative, right? So we can say f prime of A is less than 0. Right? Does everyone agree with that? Okay, how about at B? It's also negative, right? Right? Now, but let's compare f prime of A and f prime of B. Is there anything we can say there? F prime of A is more negative than f prime of B, right? So how can we write that? F prime of B, this, right? Right? That's true, right? Okay, then what about at C? F prime of C is also negative, right? And that is, I guess, like this, right? Consider that, right? Right? Everyone agree? Because less negative than B. And then, of course, at D, it's flat. And how about at E? At E, f prime of E is positive, right? And f prime of G is also positive, right? And f prime of H is also positive, right? Okay, so everyone agrees with all these, right? Okay, so what's happening to the derivative? It starts out very negative, becomes less negative, becomes less negative, but still negative, becomes 0, becomes positive, and more positive. Positive and more positive, right? So if something starts out negative, less negative, positive, more positive, what will you say about it? Yeah, I might say it's a problem, but what else might you say about it? If, let's say, my debt starts out very negative, or let's say my bank account. Let's say my bank account starts out very negative, less negative, 0, positive, more positive. It's what? Yeah, my bank account is increasing, right? Right? If something starts out very negative, becomes less negative, 0, and positive, more positive, it's increasing, right? What is increasing here? What were we just talking about? F prime, right? The derivative is increasing, right? Do you agree? Can I say that? Between A and G or H, whatever it is, the derivative is increasing, right? So when a function is concave up, the derivative is always going to be doing that, right? It's going to be increasing, right? If it's going like that, the derivative is going to be increasing, right? So let's write that down. Concave up, I'll write it like that, implies f prime is increasing. Do you agree or not? Not f. F prime is increasing, right? Okay? And I think probably we can write this direction also. If f is increasing, if f prime is increasing, then it's concave up. Okay? And I think the other way is going to be obviously just the opposite, right? If it's here, the slope is decreasing, and that's concave down. So let's write that. Concave down, f prime is decreasing. Do everyone agree with that? Okay, now here's the trick. Do you remember this trick? this statement rather. So let's write the bottom one once more. I'll write it over here. I'll write it here. What did the bottom one say? If f is increasing, or let's just write it sort of the way I just wrote the other one. So f increasing what? What does it say? F increasing, then what? F prime is greater than 0. Right? Okay, now the question is, how can we combine these two statements? Now it looks like they can't be combined, because this is talking about f prime increasing, and here we have f increasing, so they look like they don't really have anything to do with each other, right? 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 You can't really work with them together, right? Okay, that's right, you can't work with them together. However, let's focus on this for a moment. This says what? F is increasing, then f prime is greater than 0, right? That's true for any f, right? For any f, right? Of course it's true for any f. Okay, now let me ask you something. Is f prime a function? Is it a function or not? Yeah, it's a function, right? It's going to be some function, right? Okay, so let me write this. Instead of writing f here, let's say